Tonight, we're going to follow the journey of the most distant human-made object ever created, Voyager 1. Right now, as you're watching this, Voyager 1 is hurtling through interstellar space at over 38,000 miles per hour, more than 15.5 billion miles from Earth. It's been traveling for over 48 years, and it's still going. But here's what most people don't realize. Voyager 1 is dying. Slowly, inevitably, its power is fading, its systems are shutting down, and one day very soon, it will go silent forever. And by the end of tonight, you're going to understand exactly how far this spacecraft can travel before it runs out of power, what will happen when it finally goes dark, and where it will be billions of years from now, long after humanity itself might be gone. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what Voyager 1 actually is, because it's not just some random spacecraft drifting through space. It's a time capsule, an ambassador, and one of humanity's most remarkable achievements, all rolled into a machine about the size of a small car. Voyager 1 launched on September 5, 1977, from Cape Canaveral, Florida. It weighed about 1,592 pounds at launch, and it was built to do something that had never been done before: visit the outer planets of our solar system. The spacecraft was designed during a unique planetary alignment that happens only once every 176 years. This alignment allowed Voyager to use a technique called gravity assist, where it would swing by one planet and use that planet's gravity to slingshot itself toward the next one. Without this alignment, the mission wouldn't have been possible with the technology available at the time. The journey would have taken decades longer and required far more fuel than any spacecraft could carry. Voyager 1's primary mission was to study Jupiter and Saturn, their moons, their rings, and their magnetic fields. It accomplished this brilliantly, sending back thousands of images and scientific measurements that completely transformed our understanding of the outer solar system. But after Saturn, something interesting happened. The mission didn't end. Voyager 1 kept going, and NASA kept listening. What was supposed to be a 5-year mission became a 48-year journey and counting. Today, Voyager 1 holds the record as the most distant human-made object from Earth. And it's still sending data back to Earth, though that data takes over 21 hours to reach us, traveling at the speed of light across the vast emptiness of interstellar space. To understand how far Voyager can go before it dies, we need to understand what keeps it alive. And the answer to that is both elegant and terrifying in its simplicity. Voyager 1 is powered by heat. Specifically, it's powered by something called a radioisotope thermoelectric generator, or RTG for short. An RTG is not a battery in the conventional sense. It doesn't store energy that was put into it. Instead, it generates electricity from the heat produced by radioactive decay. This might sound dangerous, but it's actually one of the safest and most reliable power sources ever developed for space exploration. Inside Voyager 1, there are 3 RTGs, each containing pellets of plutonium-238. Each RTG is about the size of a small trash can, and they're mounted on a boom that extends out from the main spacecraft body. This boom keeps the RTGs away from the sensitive scientific instruments because the radioactive decay also produces a small amount of radiation that could interfere with measurements. Plutonium-238 is radioactive, and as it decays, it releases heat. Specifically, it releases alpha particles, which are helium nuclei consisting of 2 protons and 2 neutrons. These alpha particles don't travel far before they're absorbed by the surrounding material, and when they're absorbed, their kinetic energy is converted into heat. That heat is converted into electricity using thermocouples, devices that generate voltage when one side is hot and the other side is cold. It's based on something called the Seebeck effect, discovered in the 1820s by German physicist Thomas Johann Seebeck. When you have 2 different metals connected in a circuit and you heat one junction while keeping the other cool, you get an electrical current. The temperature difference drives electrons to flow from the hot side to the cold side, creating voltage. Voyager's thermocouples use semiconductor materials rather than simple metals, because semiconductors are more efficient at converting heat to electricity, but the principle is the same. Hot on one side, cold on the other, and you get power. It's a beautifully simple system with no moving parts, no chemical reactions that can run out, no solar panels that can get covered in dust or damaged by radiation. Just heat, thermocouples, and electricity. The beauty of this system is its reliability. There are no motors to seize up, no gears to wear out, no batteries to degrade through charge-discharge cycles. As long as the plutonium is decaying, which it will do for thousands of years, the RTGs produce heat. And as long as there's a temperature difference between the hot side and the cold side, which there will be in the freezing vacuum of space, the thermocouples produce electricity. It's passive, reliable, and predictable. The engineers who designed Voyager knew exactly how much power the RTGs would produce at launch, and they could calculate exactly how that power would decline over time based on the half-life of plutonium-238. This predictability has been crucial for mission planning. NASA has always known that Voyager's power would decline, and they've planned for it from the very beginning. The alternative would have been solar panels, but solar panels don't work well in the outer solar system. The sun's light gets weaker the farther you travel from it. At Earth's distance, sunlight delivers about 1,368 watts per square meter. At Jupiter's distance, about 5 times farther from the Sun, that drops to only about 50 watts per square meter. At Saturn's distance, it's only 15 watts per square meter, and at Neptune's distance, it's less than 2 watts per square meter. To power Voyager with solar panels at Neptune, you'd need panels the size of a tennis court, and they'd be useless once Voyager left the solar system and entered interstellar space. RTGs were the only practical choice. They work anywhere, regardless of how far you are from the sun, regardless of whether you're in sunlight or shadow. They just keep producing power, year after year, decade after decade. The Soviet Union used RTGs extensively in their lunar and Lunokhod missions to the moon. The United States used them on the Apollo lunar surface experiments, the Viking Mars landers, the Pioneer spacecraft, the Cassini mission to Saturn, the New Horizons mission to Pluto, and the Curiosity and Perseverance Mars rovers. RTGs are proven technology, and they've never failed in space. Every single RTG that has been launched has worked exactly as designed. When Voyager 1 launched in 1977, its 3 RTGs produced about 470 watts of electricity. That's about the same amount of power as 5 old-fashioned incandescent light bulbs. Not much, but enough to run the spacecraft's systems, its computers, its instruments, its radio transmitter. For perspective, your smartphone probably uses about 5 to 10 watts when you're actively using it. Your laptop might use 30 to 60 watts. A desktop computer might use 200 to 300 watts. Voyager had to run an entire spacecraft with multiple scientific instruments, a computer, attitude, control thrusters, a radio transmitter powerful enough to send signals across billions of miles, all on less power than it takes to run a modern desktop computer. The engineering required to make this work is staggering. Every component had to be designed for extreme efficiency. Every watt had to be carefully budgeted. There was no margin for waste. But here's the problem. Plutonium-238 decays over time. It has a half-life of about 87.7 years, which means that every 87.7 years, half of the plutonium atoms will have decayed into other elements. After 87.7 years, Voyager's RTGs would produce half the power they started with. After 175.4 years, they'd produce a quarter of the original power, and so on. The power output decreases exponentially over time. This is not linear decline. It's not like the RTGs lose the same amount of power every year. Instead, they lose a percentage of their current power every year. The rate of decline itself slows down over time because there's less and less plutonium left to decay. In the first year, Voyager lost more watts of power than it does today because it had more plutonium decaying. Today, with less plutonium remaining, it loses fewer absolute watts per year, but the percentage decline relative to the current power output stays roughly constant. Now, Voyager 1 hasn't been out there for 87.7 years yet. It's only been traveling for about 48 years, but the power has still declined significantly. Currently, Voyager 1's RTGs produce about 220 watts of electricity, less than half of what they produced at launch. That's down from 470 watts to 220 watts over 48 years. And that number drops by about 4 watts every single year. Every year, Voyager gets a little bit weaker. Every year, it has a little less power to work with. And every year, NASA has to make harder and harder decisions about which systems to keep running and which ones to shut down, because the spacecraft needs a minimum amount of power to function, and it's approaching that minimum. The question isn't whether Voyager will run out of power, it's when, and the answer, based on current projections, is sometime in the mid to late 2030s. By then, the RTGs will be producing so little power that even the most essential systems won't be able to operate. The radio transmitter, which currently uses about 28 watts, will no longer have enough power to function. The computer, which manages all the spacecraft systems, will shut down. The attitude control system, which keeps Voyager pointed toward Earth so it can transmit data, will stop working. One by one, everything will go dark. And when the power drops below a critical threshold, estimated to be around 60 to 70 watts total, the spacecraft will essentially be dead from an operational standpoint. It will still be producing some power, but not enough to do anything useful with it. The RTGs will continue to decay, continue to produce heat, continue to generate tiny amounts of electricity, but it won't be enough to run even a single system. Voyager will be a derelict, drifting through space with power generation equipment that no longer serves any purpose. The decline in power isn't the only problem Voyager faces. There's also the issue of degradation. Voyager 1 has been in space for nearly half a century. It's been exposed to cosmic radiation, extreme temperature variations, micrometeoroids, and the vacuum of space. All of this takes a toll. The spacecraft experiences temperature swings that would destroy most electronic equipment. When it's in direct sunlight, parts of the spacecraft can reach temperatures well above the boiling point of water. When it's in shadow, temperatures can drop to nearly absolute zero. These thermal cycles cause materials to expand and contract, creating stress on joints, welds, and electronic connections. Over 48 years, these cycles add up. Solder joints can crack. Wire connections can weaken. Mechanical parts can develop tiny fractures. Cosmic radiation is another major problem. Out in interstellar space, Voyager is bombarded constantly by high-energy particles. These particles come from supernova explosions, from the Sun, from other stars, even from outside our galaxy. When a high-energy particle strikes an electronic component, it can flip bits in computer memory, cause circuits to malfunction, or even permanently damage semiconductor junctions. This is called single-event upset, and it's a constant threat to spacecraft electronics. Voyager's computer has experienced countless single-event upsets over the years. Most of them are temporary. The computer detects the error and corrects it. But some cause permanent damage, degrading the performance of circuits over time. The thermocouples that convert heat into electricity have degraded over time. They're less efficient now than they were in 1977. This means that even if the RTGs were producing the same amount of heat, they would generate less electricity because the conversion process is less efficient. The degradation of thermocouples is actually a bigger factor in Voyager's power decline than the decay of plutonium. At 48 years into the mission, thermocouple degradation accounts for roughly half of the power loss. The other half is due to the radioactive decay of plutonium-238. This was not entirely unexpected. Engineers knew that thermocouples would degrade in the space environment. They just didn't know exactly how fast or how severe the degradation would be because no spacecraft had ever operated for this long in deep space before. Voyager is literally testing the limits of what's possible with 1970s technology. The spacecraft's components have also degraded. Electronic circuits that were designed in the 1970s using technology that seems primitive by today's standards have been operating continuously for decades in an environment they were never designed to withstand for this long. Voyager's computer has 64 kilobytes of memory. That's 64,000 bytes, not megabytes or gigabytes. For comparison, a single high-resolution photograph from a modern smartphone is larger than Voyager's entire memory capacity. The computer's processor runs at a clock speed of about 250 kilohertz. A modern smartphone processor runs at speeds measured in gigahertz, millions of times faster. And yet, this tiny, slow computer has been managing Voyager's systems for 48 years. It controls the spacecraft's orientation, manages the scientific instruments, handles data compression and storage, and communicates with Earth. All with 64 kilobytes of memory and a processor that runs slower than a calculator from the 1980s. Some of these components have failed over the years. Others are on the verge of failure, and there's no way to repair them. No astronaut can fly out to Voyager and swap out a broken circuit board. No technician can replace a degraded thermocouple. Once something breaks, it stays broken. The spacecraft's attitude control system, which keeps Voyager pointed in the right direction, relies on thrusters that fire tiny bursts of hydrazine fuel. Hydrazine is a chemical compound that ignites when it comes into contact with a catalyst. No spark needed, no ignition system. Just bring the fuel into contact with the catalyst and it burns. This makes hydrazine thrusters extremely reliable. which is why they've been used on almost every spacecraft ever built. Voyager has 16 small thrusters arranged around its body. They're used to rotate the spacecraft, to point the antenna toward Earth, to make small adjustments to the trajectory. These thrusters are also aging. They're not as responsive as they used to be, and the fuel lines have degraded, causing clogs and reduced efficiency. The fuel lines are made of a type of rubber that remains flexible at extremely cold temperatures. But after 48 years in space, that rubber has become brittle and cracked in places. Some of the fuel lines have developed tiny leaks. Others have become partially clogged with residue from the hydrazine fuel. This means that when Voyager's computer sends a command to fire a thruster, the response isn't as quick or as precise as it used to be. The thruster might take longer to start firing, or it might produce less thrust than expected. NASA has had to switch to backup thrusters several times over the years. Thrusters that were originally designed to be used during planetary flybys, not for continuous operation in interstellar space. In 2017, NASA made the decision to switch from the primary attitude control thrusters to the trajectory correction maneuver thrusters. These backup thrusters hadn't been fired in 37 years, not since Voyager's encounter with Saturn in November 1980, when NASA reactivated them in 2017. The engineers weren't even sure if they would still work after sitting dormant for nearly 4 decades. But they did. On November 28, 2017, NASA sent the command to fire the trajectory correction thrusters. 20 hours later, the signal reached Voyager. The thrusters fired, and 20 hours after that, the confirmation signal reached Earth. It worked. The dormant thrusters came to life and functioned perfectly. It was a remarkable achievement, a testament to the quality of the engineering that went into Voyager. But even those backup thrusters are now showing signs of wear. In 2020, NASA noticed that the trajectory correction thrusters were starting to degrade, requiring more power and producing less thrust. So they switched back to the primary attitude control thrusters, which had been resting for 3 years and had partially recovered. This thruster management game is one of the many challenges NASA faces in keeping Voyager alive. They're constantly juggling limited resources, trying to squeeze out every last bit of performance from aging hardware. And even with all this careful management, they know they're fighting a losing battle. The thrusters will eventually fail completely. The fuel lines will become too clogged to function. The computer will experience one error too many and crash permanently. The thermocouples will degrade to the point where they can't produce enough electricity, even if the RTGs are still generating heat. It's just a matter of time. The spacecraft's radio transmitter, which sends data back to Earth, is also weakening. The signal that reaches Earth from Voyager 1 is incredibly faint. It's about 20 billion times weaker than the power required to run a digital watch. To put that in perspective, if you took all the energy that Voyager's transmitter sends toward Earth over the course of a year and collected every single photon that reaches Earth, you'd have barely enough energy to heat a cup of coffee by 1 degree. That's how weak the signal is. To detect this signal, NASA uses enormous radio dishes, some of the largest and most sensitive in the world, part of the Deep Space Network. The Deep Space Network consists of 3 facilities located around the world, in California, Spain, and Australia. Each facility has multiple radio dishes, with the largest being 70 meters in diameter. That's 230 feet, about the height of a 20-story building. These dishes can detect radio signals so faint that they're billions of times weaker than the background radiation from the Big Bang that fills all of space. Even with these massive dishes, the signal from Voyager is barely detectable. The data rate has been reduced over the years as the signal has weakened. Currently, Voyager transmits at about 160 bits per second. For comparison, a typical home internet connection can download data at rates of 100 million to 1 billion bits per second. Voyager's data rate is about 600,000 to 6 million times slower. It takes hours for Voyager to transmit what your internet connection could download in a fraction of a second. But that 160 bits per second is enough to send back scientific data, telemetry, information about the spacecraft's health, and status updates. It's a trickle of information, but it's precious. Every bit that makes it back to Earth represents a triumph over the vast distances and the limited power available to the spacecraft. And as Voyager gets farther away and its power decreases, the signal will get even weaker. Eventually, it will become too weak to detect at all, even with the most sensitive equipment on Earth. When that happens, we'll lose Voyager forever. Not physically, it will still be out there, still moving, still existing, but we won't be able to hear it anymore. It will have passed beyond the reach of our technology. NASA has been managing Voyager's declining power for decades now, and they've done an incredible job of keeping the spacecraft alive far longer than anyone expected. But it's a constant balancing act. Every few years, they have to shut down another system to conserve power. In 2007, they turned off the plasma subsystem instrument. This was one of Voyager's scientific instruments, used to study charged particles in space. It had been running since launch, but it had to go to save power. In 2008, they turned off the planetary radio astronomy instrument. This instrument was designed to detect radio emissions from planets like Jupiter. It was no longer needed because Voyager had left the planets far behind, so it was shut down. In 2016, they had to make another tough decision. They turned off one of the heaters that kept the instruments warm. This was risky because the instruments were never designed to operate at such low temperatures. But it worked. The instruments survived, and the power was conserved. In 2019, they shut down another heater, this time for the cosmic ray instrument. Again, the instrument survived the cold and continued to function. Each shutdown buys Voyager a little more time, a few more years of operation. But each shutdown also means less data, fewer instruments, less capability. Voyager is being stripped down piece by piece, like a ship throwing cargo overboard to stay afloat a little longer. Currently, Voyager 1 has only 4 scientific instruments still operating. The cosmic ray subsystem, which detects high-energy particles from outside the solar system. The low-energy charged particle instrument, which measures the flow of charged particles in interstellar space. The magnetometer, which measures magnetic fields. And the plasma wave subsystem, which detects plasma oscillations and radio emissions. These 4 instruments are all that's left of Voyager's scientific payload. Everything else has been shut down to save power. But even these 4 instruments won't last forever. NASA estimates that they'll have to start shutting down instruments permanently in the next few years. By around 2028 to 2032, Voyager will likely have lost all of its scientific instruments. It will still be able to transmit a carrier signal, a simple radio tone that says, "I'm still here," but it won't be able to send any scientific data. And by around 2036, maybe a few years earlier, maybe a few years later, depending on how efficiently they can manage the remaining power, Voyager 1 will fall silent completely. It will run out of power. The RTGs will still be producing some heat, but not enough to generate the electricity needed to run even the most basic systems. The radio transmitter will shut down. The computers will stop functioning. The spacecraft will go dark, and humanity will lose contact with Voyager 1 forever. So, how far can Voyager 1 travel before it dies? Well, it depends on what you mean by dies. If you mean when will it stop sending scientific data, that will probably happen sometime in the next few years, around 2029 to 2032. At that point, Voyager will be about 15 to 16 billion miles from Earth. If you mean when will it stop transmitting any signal at all, including just a carrier tone, that will happen around 2036, give or take a few years. At that point, Voyager will be about 17 to 18 billion miles from Earth. 17 to 18 billion miles. That's the distance it will travel before it truly dies. But just because Voyager stops transmitting doesn't mean it stops moving. The spacecraft will continue traveling through space for billions of years. It's moving at about 38,000 miles per hour relative to the Sun. That might not sound fast compared to the speed of light, which is about 670 million miles per hour, but it's incredibly fast by human standards. A commercial airliner cruises at about 570 miles per hour. Voyager is moving about 67 times faster than that, and it's not slowing down. There's no air resistance in space, no friction to slow it down. Once an object is set in motion in the vacuum of space, it will keep moving at the same speed forever unless something acts on it. And out in interstellar space, there's almost nothing to act on Voyager. There's the incredibly faint pull of gravity from distant stars, but it's so weak that it barely affects the spacecraft's trajectory. There's the interstellar medium, the thin gas and dust that exists between stars, but it's so diffuse, less than 1 atom per cubic centimeter on average, that it creates virtually no drag. Voyager will keep moving at 38,000 miles per hour for thousands, millions, billions of years. It will outlast the Sun. The Sun has about 5 billion years of life left before it exhausts its hydrogen fuel and begins to expand into a red giant. When that happens, it will swallow Mercury, Venus, and possibly Earth. But Voyager will be long gone, far beyond the reach of the dying Sun's expansion. It will outlast the solar system. Eventually, the planets will be scattered or absorbed as the Sun goes through its final death throes and becomes a white dwarf. But Voyager will still be out there, drifting silently through the galaxy. It will even outlast the current configuration of the galaxy. The Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, the two galaxies will merge, creating a new, larger galaxy. The stars and gas clouds will be scrambled, orbits will change, but Voyager will continue its journey through whatever new structure emerges. Barring an incredibly unlikely collision with a star or another object, Voyager 1 will drift through space, essentially forever. Billions of years from now, when humanity is long extinct, when Earth is a cold, dead rock, when the Sun is a fading white dwarf, Voyager will still be out there. A tiny, silent artifact of a civilization that once looked up at the stars and wondered what was out there. One of the most fascinating aspects of Voyager's journey is its trajectory. Where exactly is it going? Voyager 1 isn't aimed at any particular star. It's traveling in a direction roughly toward the constellation Ophiuchus, the Serpent Bearer. one of the 13 constellations that lie along the ecliptic. The path the Sun appears to follow through the sky over the course of a year. Ophiuchus is wedged between Scorpius and Sagittarius, and despite being on the ecliptic, it's not one of the traditional 12 zodiac constellations. That's because the zodiac was defined thousands of years ago when the precession of Earth's axis was different and the ecliptic passed through different parts of Ophiuchus than it does today. But for our purposes, what matters is that Voyager is headed in that direction, toward a part of the sky that's relatively unremarkable from Earth's perspective. There's no bright star in that direction that Voyager is aiming for, no exotic destination that the mission planners selected. Voyager is simply moving in the direction it was flung by its encounter with Saturn back in November 1980. After flying past Saturn, the spacecraft's trajectory was determined by the gravitational interaction with the planet. Saturn's gravity pulled Voyager 1 upward, relative to the plane of the solar system, and flung it out into interstellar space at an angle of about 35 degrees above the ecliptic. This trajectory is permanent. There's nothing out there to change it. Voyager will continue moving in essentially the same direction for millions of years. In about 40,000 years, it will pass within about 1.6 light-years of a star called Gliese 445, also known as AC plus 79 degrees, 3,888. This is a red dwarf star, much smaller and dimmer than our Sun, with a mass of about 0.16 solar masses. It's currently about 17.1 light-years away from Earth, moving through space at about 75 miles per second relative to the Sun. This motion will bring it closer to Voyager's path, and in 40,000 years, the two will have their closest approach. 1.6 light-years is relatively close by cosmic standards, though still an enormous distance. 1.6 light-years is about 9.4 trillion miles. To put that in perspective, if you could shrink the distance down so that 1 mile represented 1 inch, 1.6 light-years would be about 150,000 miles, more than half the distance from Earth to the Moon. Voyager will zip past this star, much too far away to be affected by its gravity, and continue on its way. The star itself is so dim that even if Voyager had functioning cameras, which it doesn't anymore, Gliese 445 would just be another point of light in the sky, perhaps slightly brighter than the background stars, but not dramatically so. Red dwarfs are the most common type of star in the galaxy, making up about 70 to 80% of all stars. But they're also the dimmest, so none of them are visible to the naked eye from Earth. Proxima Centauri, the nearest star to the Sun, is a red dwarf, and it's too faint to see without a telescope, even though it's only 4.24 light-years away. Gliese 445 is even dimmer and farther away, so from Earth it's completely invisible except to large telescopes. After passing Gliese 445, Voyager will continue on through the galaxy for millions and millions of years, never coming particularly close to any other star. The next close encounter won't happen for hundreds of thousands or millions of years. Space is just too vast. The distances between stars are so enormous that random encounters are extraordinarily rare. Let's think about the scales involved here. The average distance between stars in our part of the galaxy is about 4 to 5 light-years. That's about 24 to 29 trillion miles. If you imagine the stars as grains of sand, the average spacing between them would be about 60 miles. Now imagine throwing a single grain of sand randomly into that space and asking, what are the chances it hits another grain of sand? The answer is effectively zero. You could throw trillions of grains of sand and never hit anything. That's the situation Voyager is in. It's a tiny object moving through a space so vast that encounters with anything are almost impossible. The chances of Voyager ever colliding with a star are essentially zero. It's like throwing a grain of sand into the ocean and expecting it to hit a specific fish. Even over billions of years, the odds don't improve much. The galaxy is just too vast, and Voyager is just too small. There's a slightly better chance that Voyager might pass through a molecular cloud, a dense region of gas and dust where new stars are forming. Molecular clouds are huge, sometimes hundreds of light years across, and they contain enough material to make thousands or millions of stars. If Voyager passes through one of these clouds, it would experience a slight drag from the gas and dust. Not enough to noticeably slow it down, but enough that if you were measuring its velocity precisely, you might detect a tiny deceleration. The density of a molecular cloud is still incredibly low by Earth standards. The densest parts might have 10,000 to 1 million particles per cubic centimeter. That sounds like a lot. But for comparison, the air you're breathing right now has about 25 quintillion particles per cubic centimeter. A molecular cloud is about 1 trillion times less dense than air. So, even if Voyager passes through one, the drag would be minimal. Over millions of years, it might slow down by a few meters per second, but that's all. The most likely fate for Voyager is that it will drift through space forever, or at least for many billions of years, until eventually the materials it's made of begin to degrade from cosmic radiation and quantum effects. This brings us to a deep question. What happens to matter over extremely long timescales? We know that matter is made of atoms, and atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks, held together by the strong nuclear force. The question is, are protons stable forever, or do they eventually decay? Current experimental limits suggest that if protons do decay, they have a half-life of at least 10 to the 34 years. That's a 1, followed by 34 zeros. For comparison, the current age of the universe is about 13.8 billion years, which is 1.38 times 10 to the 10th years. Proton decay, if it happens, occurs on timescales that are trillions of trillions of trillions of times longer than the current age of the universe. If protons do decay with a half-life of 10 to the 34 years, then after 10 to the 34 years, half of the protons in Voyager will have decayed. After 2 times 10 to the 34 years, half of the remaining protons will have decayed, and so on. Eventually, after many half-lives, essentially all of Voyager's protons will have decayed into lighter particles and radiation. At that point, Voyager will truly cease to exist as a physical object. It will have disintegrated at the atomic level, its matter converted into photons, and perhaps exotic particles like neutrinos or other quantum remnants. But that's so far in the future that it's almost meaningless to think about. For all practical purposes, for timescales that we can actually wrap our minds around, Voyager will exist forever. 1 billion years from now, Voyager will still be out there, dark and silent, but still physically intact. 10 billion years from now, long after the sun has died and become a white dwarf, Voyager will still be drifting. 100 billion years from now, when most of the stars in the galaxy have burned out, and the Milky Way has merged with Andromeda and other nearby galaxies, Voyager will still be there. It's a monument to the species that built it, a physical artifact that will outlast not just humanity, but our entire planet, our star, and possibly our galaxy as we know it. And it's carrying the golden record, that 12-inch disc of gold-plated copper with sounds and images from Earth. The record itself should remain readable for hundreds of millions of years at least, possibly billions of years. Gold doesn't corrode in the vacuum of space. The information encoded on it is analog, etched into the surface as physical grooves. As long as the physical structure of the record remains intact, the information can be recovered. Cosmic ray damage will eventually degrade the surface, creating pits and scratches that could make parts of the record unreadable. But this process is slow, occurring over timescales of millions or billions of years. For a very, very long time, the golden record will remain a pristine archive of Earth's biosphere and culture, frozen in time at the moment of Voyager's launch in 1977. Anyone who finds it, whether in 1,000 years or 1 billion years, will be able to decode the images and sounds and learn about a planet called Earth and the species that inhabited it. They'll hear human voices speaking dozens of languages. They'll hear music from cultures spanning the globe. They'll see images of our cities, our families, our world. They'll know that we existed. They'll know that we wondered about the cosmos. And they'll know that we dared to reach out, to send a message across the void, hoping that someone, somewhere, might receive it. That's the legacy of Voyager. Not the scientific discoveries, as important as those are. Not the technological achievement, as impressive as that is. But the simple fact that we tried. We built a machine, put it on a rocket, and sent it to the stars. We attached a message saying, "We were here. This is who we were. Remember us." And that message will outlast everything else we've ever done. Let's talk about what Voyager is carrying, because this spacecraft isn't just a scientific instrument. It's also a message. Attached to Voyager 1, and its twin Voyager 2, is a golden record. The Voyager Golden Record is a 12-inch gold-plated copper disc that contains sounds and images selected to portray the diversity of life and culture on Earth. It was curated by a committee chaired by Carl Sagan, the famous astronomer and science communicator. Sagan assembled a team that included Frank Drake, the astronomer who developed the Drake equation for estimating the number of intelligent civilizations in the galaxy; Anne Druyan, a writer and producer who later became Sagan's wife; Timothy Ferris, a science writer and filmmaker; John Lomberg, an artist who specialized in astronomical art; and several other scientists, artists, and musicians. Together, they had the daunting task of selecting sounds and images that would represent all of humanity to a potentially alien audience. How do you choose what to include when you only have space for 116 images and about 90 minutes of audio? What pieces of music represent human culture? What sounds capture the essence of Earth? What images show what life is like on our planet? The committee debated for months. Every choice was agonizing, because every inclusion meant something else had to be left out. The record includes greetings in 55 different languages, from ancient Sumerian to modern Chinese. The greetings are simple, usually just "hello" or "peace" or "greetings from the people of Earth," but hearing them all together is moving. There's something profound about hearing voices speaking in languages from across the globe, all united in the act of reaching out to the unknown. The first greeting on the record is in Sumerian, one of the oldest written languages known to humanity. It says, "May all be well." The last greeting is in Wu, a Chinese dialect. It says, Hi, how are you? Wish you peace, health, and happiness. In between are greetings in languages ranging from Arabic to Zulu, from Russian to Hindi, from French to Japanese. Some of the languages, like Latin and ancient Greek, are no longer spoken in daily life, but represent important parts of human history. Others, like Mandarin, Chinese, Spanish, and English, are spoken by hundreds of millions of people. The diversity is intentional, a statement that Earth is home to many cultures, many languages, many ways of being human. The record includes sounds from nature, like thunder, waves, bird calls, and whale songs. There's the sound of wind, rain falling, surf crashing on a beach. There's the crackling of a fire, the chirping of crickets at night, the songs of birds greeting the morning. These natural sounds are meant to convey what Earth sounds like, the acoustic environment of a living planet. There are also human sounds, footsteps, laughter, a baby crying, a kiss. The sound of a human heartbeat plays for several seconds, a rhythmic thump-thump that's universal to all humans, regardless of culture or language. The record includes music from around the world, from Beethoven to Chuck Berry, from traditional Japanese music to African drumming. The music selection was particularly controversial. How do you represent all of human musical achievement with just 90 minutes of audio? The committee chose pieces that they felt represented the diversity and depth of human musical expression. There's Bach's Brandenburg Concerto, No. 2, a masterpiece of Baroque music from the early 1700s. There's Beethoven's Fifth Symphony, one of the most famous pieces of classical music ever written. There's Mozart's Queen of the Night aria from the Magic Flute, showcasing the incredible range and skill of the human voice. But there's also Chuck Berry's Johnny Be Good, a rock and roll song from 1958 that captures the energy and rebellious spirit of American youth culture in the mid-20th century. There's Dark Was the Night, Cold Was the Ground by Blind Willie Johnson, a blues song from 1927 that expresses profound emotion with just a guitar and a voice. There's traditional music from Java, Peru, Senegal, Bulgaria, India, and many other cultures. There's a Navajo night chant, a Japanese shakuhachi piece, Australian Aboriginal songs, and a Georgian folk song. The committee tried to include music that was not only technically sophisticated, but also emotionally powerful. They wanted music that would convey the depth of human feeling, our capacity for joy, sorrow, love, and transcendence. Anne Druyan later described the process of selecting the music as one of the most difficult tasks she'd ever undertaken. Every piece they chose meant dozens of other worthy pieces had to be left out. She said it was like being asked to represent all of human art with just a tiny sample, knowing that whatever you chose would inevitably be incomplete and imperfect. The record also includes 116 images encoded in analog form. These images were encoded as audio signals that can be decoded and displayed as pictures if the aliens figure out the encoding scheme. The images show everything from mathematical diagrams to photographs of humans, animals, landscapes, and buildings. There are diagrams showing the structure of DNA, the double helix that carries the genetic information for all life on Earth. There are images of cells dividing, showing the process of mitosis that allows organisms to grow and reproduce. There are images of human anatomy, showing the structure of our bodies. There are pictures of conception and birth, the beginning of human life. There are images of families, showing parents with children, capturing the bonds that hold human societies together. There are images of people from different cultures, wearing different clothing, engaged in different activities. A Guatemalan weaver, a Balinese dancer, an Andean flute player, demonstrating the diversity of human cultural expression. There are images of cities and buildings, showing what human civilization looks like. The Great Wall of China, one of the largest structures ever built by humans. The Taj Mahal, a monument to love and architectural beauty. Modern cities with skyscrapers and highways, showing the technological society that built Voyager. There are images of nature, forests and oceans and mountains and deserts, showing the environments that exist on Earth. There are images of animals, an eagle in flight, a dolphin leaping from the water, an elephant, a gorilla, creatures that share our planet. There are images of food, a feast laid out on a table, showing that humans not only eat to survive, but create complex social rituals around food. And there are images of human achievements, the Olympic athlete running, demonstrating our capacity for physical excellence. The Titan Centaur rocket launching, the same type of rocket that launched Voyager, showing our ability to reach into space. One of the images is a photograph of Andruyan's brain activity. This might sound strange, but hear me out. The committee wanted to include some representation of human thought and consciousness on the record. They considered including brainwave recordings, the electrical signals produced by neurons in the human brain. Andruyan volunteered to have her brain activity recorded for 1 hour while she meditated on various topics. The history of Earth, the evolution of life, human societies, mathematics, falling in love. The recording was made on June 1st, 1977, just a few weeks before Voyager's launch. Druyan later described it as one of the most meaningful experiences of her life, knowing that her thoughts at that moment would be encoded on a record that would outlast Earth itself. The recording of her brainwaves is on the Golden Record, a direct representation of human consciousness in all its complexity. Whether an alien civilization could ever decode and understand it is questionable. But it's there, nonetheless. A recording of a human mind thinking about the universe and its place in it. The idea was that if Voyager is ever found by an intelligent extraterrestrial civilization, they would be able to decode the record and learn about the people who built it. There are even instructions etched onto the cover of the record showing how to play it and where it came from. The cover shows a diagram of our solar system with the trajectory Voyager took past the outer planets. It shows Jupiter, Saturn, and the path Voyager followed to reach them. This diagram tells anyone who finds it where the spacecraft came from and what route it took to get where it is. The cover also shows the position of the Sun relative to 14 pulsars, rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses. Each pulsar rotates at a specific frequency, measured in milliseconds, and these frequencies are unique. They're like cosmic barcodes that can be used to identify location and time. The diagram shows lines radiating out from the Sun, each line pointing toward a specific pulsar. The length of each line represents the distance to that pulsar, and there's a binary number next to each line indicating the pulsar's rotation period. Any sufficiently advanced civilization could use this map to locate the solar system. They would measure the rotation periods of pulsars in their vicinity, match them to the periods encoded on the diagram, and triangulate the position of the Sun. It's an elegant solution to the problem of communicating location across interstellar distances. But there's a catch. Pulsars slow down over time as they lose rotational energy. Their periods gradually increase. So the pulsar map will only be accurate for a certain period of time, probably a few million years. After that, the pulsar periods will have changed enough that the map becomes ambiguous. This actually tells us something interesting. If an alien civilization finds Voyager and uses the pulsar map to locate its origin, they can also calculate roughly when the spacecraft was launched based on the pulsar periods encoded on the map and their current measured periods. It's like a timestamp, encoded in the structure of the galaxy itself. The record also includes a diagram showing how to play it, the correct speed, the correct stylus placement, everything needed to extract the audio and visual information. The diagram shows a side view of the record with a stylus in the groove, indicating that it should be played like a phonograph record. It shows the proper rotation speed in terms of the fundamental transition of the hydrogen atom, a universal constant that any technological civilization would know. There's even a piece of the record stylus material included with the record, a little sample of uranium-238 encased in aluminum. Uranium-238 has a half-life of about 4.5 billion years, and it decays into lead-206 at a known rate. By measuring the ratio of uranium to lead in the sample, an alien civilization could determine how long ago the record was made, giving them another independent timestamp. Of course, the chances of Voyager ever being found are vanishingly small. The spacecraft is tiny, about the size of a small car, and space is unimaginably vast. It would take an incredible stroke of luck for an alien civilization to stumble upon it. Even if intelligent aliens exist in our galaxy, the odds of them happening to be in the right place at the right time to intercept Voyager are astronomically low. To put it in perspective, if you scattered a few dozen grains of sand randomly across the entire Earth and then asked someone to find one specific grain, their chances would be better than an alien civilization randomly encountering Voyager. But that's not really the point. The golden record isn't primarily for aliens. It's for us. It's a statement about who we are, what we value, and what we hope to leave behind. It's a message in a bottle thrown into the cosmic ocean, more an act of hope and defiance than a practical attempt at communication. Carl Sagan said it best. The spacecraft will be encountered, and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. That hope is encoded in every groove of the golden record. The hope that we are not alone, that someone might find this artifact, that something of humanity might survive even after we're gone. It's a statement that we existed, that we created art and music and science, that we looked up at the stars and wondered what was out there, and that we had the courage and ambition to send a part of ourselves into the unknown. Nearly 50 years after Voyager's launch, the golden record is more relevant than ever. It reminds us of a time when humanity dared to dream big, when we invested in missions that would take decades to complete, when we created messages intended for beings we might never meet. It reminds us that we are capable of thinking beyond ourselves, beyond our immediate needs and desires, and creating something that will outlast our individual lives and possibly our entire civilization. The golden record is a monument to human optimism and curiosity, and as long as Voyager continues its journey through the galaxy, that monument will endure, carrying our message forward through space and time. Voyager's journey has taught us an enormous amount about the outer solar system and interstellar space. When Voyager 1 flew past Jupiter in 1979, it discovered active volcanoes on Io, one of Jupiter's moons. This was the first time active volcanism had been seen anywhere other than Earth. It completely changed our understanding of how moons could be geologically active. The discovery happened almost by accident. Linda Morabito, a navigation engineer at NASA's Jet Propulsion Laboratory, was examining images of Io to help determine Voyager's exact position. She noticed something odd in one of the images: a large umbrella-shaped cloud extending out from Io's limb, the edge of the moon as seen from Voyager. At first, she thought it might be another moon in the background, but the position didn't match any known moon. After careful analysis, the team realized they were looking at a volcanic eruption, a massive plume of material being ejected from Io's surface. The plume rose to a height of about 190 miles above Io's surface. For comparison, Mount Everest is about 5.5 miles tall. This volcanic plume was 35 times higher than the tallest mountain on Earth. Io is the most volcanically active body in the entire solar system, with hundreds of erupting volcanoes covering its surface. Some of these volcanoes produce lava flows hundreds of miles long. Others create vast lakes of molten sulfur that change color as they cool, creating a patchwork of yellows, oranges, and reds across Io's surface. This activity is driven by tidal heating. Jupiter's immense gravity, along with the gravitational tugs from Europa and Ganymede, two other large moons, constantly flexes Io's interior, generating heat through friction. Imagine bending a piece of wire back and forth repeatedly. The wire gets hot at the point where you're bending it, because the motion creates friction at the molecular level. That's essentially what's happening to Io, except on a planetary scale. Jupiter's gravity pulls Io into an elliptical orbit, so the moon gets stretched and squeezed as it orbits. When it's closer to Jupiter, the gravitational pull is stronger, and Io gets stretched out into an elongated shape. When it's farther away, the pull is weaker, and Io relaxes back toward a more spherical shape. This constant flexing generates an enormous amount of heat, enough to melt the interior and drive volcanic activity that makes anything on Earth look tame by comparison. The most powerful volcano on Earth, in terms of total energy output, is Kilauea in Hawaii. When it's actively erupting, it releases about 30 to 40 megawatts of thermal energy. Io's most powerful volcanoes release energy measured in hundreds of thousands of megawatts. They're orders of magnitude more powerful than anything on our planet. Voyager also discovered that Jupiter's Great Red Spot, a storm larger than Earth that has been observed for centuries, is incredibly complex. The Great Red Spot was first discovered in the 1600s, possibly by Giovanni Cassini in 1665 or Robert Hooke in 1664. It's been continuously observed since at least 1830, which means this storm has been raging for at least 200 years and possibly much longer. The images sent back by Voyager showed intricate cloud patterns, swirling vortices, and turbulent flows that had never been seen before. The storm rotates counterclockwise, completing one full rotation every 6 Earth days. Wind speeds at the edge of the storm reach up to 270 miles per hour. The storm is so large that you could fit 2 or 3 Earths inside it, and it extends deep into Jupiter's atmosphere, possibly down to depths of 200 miles or more. But what drives this storm? Why has it lasted for centuries when storms on Earth dissipate after a few weeks? The answer has to do with Jupiter's structure and atmosphere. Jupiter doesn't have a solid surface like Earth. It's a gas giant, composed mostly of hydrogen and helium with traces of other gases. When storms form on Earth, they eventually hit land or cold water and lose energy, causing them to dissipate. On Jupiter, there's no land to hit. The atmosphere just gets denser and denser as you go deeper, until eventually the pressure is so high that hydrogen behaves more like a liquid metal than a gas. But there's no sharp boundary, no surface to disrupt the storm. This allows storms, like the Great Red Spot, to persist for extraordinarily long periods of time. The storm draws energy from Jupiter's internal heat. The planet is still contracting very slowly from its formation 4.5 billion years ago, and this contraction releases heat. Jupiter actually radiates more energy into space than it receives from the Sun, about 1.7 times more. This internal heat drives convection in the atmosphere, creating rising and sinking columns of gas that feed energy into storms like the Great Red Spot. As long as Jupiter continues to radiate internal heat, the Great Red Spot and other long-lived storms will continue to rage. Voyager 1 also discovered that Jupiter has a ring system. Before Voyager, Saturn was the only planet known to have rings. Jupiter's rings are much fainter and much less prominent than Saturn's, which is why they weren't discovered from Earth. They're made primarily of dust, tiny particles kicked up from Jupiter's small inner moons by micrometeorite impacts. When a micrometeorite, a tiny rock traveling at high speed, hits one of these moons, it kicks up a spray of dust particles. Some of these particles fall back to the moon's surface, but others go into orbit around Jupiter, forming a ring. Jupiter's ring system consists of 4 main components. There's the halo ring, a thick torus of particles extending inward toward Jupiter. There's the main ring, a relatively bright and narrow ring that contains most of the material. And there are 2 gossamer rings, faint and diffuse structures associated with the moons Amalthea and Thebe. The entire ring system is incredibly tenuous. If you could collect all the material in Jupiter's rings and compress it into a solid sphere, it would only be a few miles across. Saturn's rings, by contrast, contain enough material to make a moon about 300 miles in diameter. Jupiter's rings are constantly being replenished by dust from the inner moons. Without this replenishment, the rings would disappear in just a few thousand years as the dust particles spiral inward toward Jupiter or get swept out of the system by solar radiation pressure. At Saturn, Voyager 1 sent back the first detailed images of the planet's rings. Scientists had known about Saturn's rings since the 1600s, when Galileo first observed them through a telescope. But Voyager revealed that the rings are far more complex than anyone had imagined. Galileo, with his primitive telescope, couldn't make out the rings clearly. He thought Saturn had 2 large moons on either side, or possibly a triple planet. He wrote, "I have observed the highest planet to be triple-bodied." It wasn't until 1655 that Christian Huygens, using a better telescope, realized that Saturn was surrounded by a ring. He described it as a thin, flat ring, nowhere touching, inclined to the ecliptic. Later observations by Cassini in the 1600s revealed that the ring was actually multiple rings with gaps between them. The largest gap, visible from Earth with a good telescope, is called the Cassini division in his honor. But Voyager showed that even this simple picture was far from complete. Instead of a few broad rings, there are thousands of individual ringlets, some braided together, some with gaps carved out by small moons, some with waves and ripples caused by gravitational interactions. The rings are made primarily of water ice, ranging in size from tiny dust particles to boulders several yards across. The ice is remarkably pure, which is why Saturn's rings are so bright and reflective. They reflect about 60 to 70% of the sunlight that hits them, making them appear brilliant white when viewed from Earth. The rings are also incredibly thin. They extend for about 175,000 miles from Saturn's center to the outer edge of the main ring system, but they're only about 30 feet thick on average. To put that in perspective, if you made a scale model of Saturn's rings with the same proportions, using a disk the size of a football field, the disk would be about as thick as a piece of paper. The rings are constantly in motion. The inner parts of the rings orbit faster than the outer parts, following Kepler's laws of planetary motion. This differential rotation creates shearing forces that can break up clumps of material and create intricate patterns. Some of the most fascinating features in Saturn's rings are the spoke-like patterns that appear and disappear over time. These spokes rotate with the rings and seem to be made of tiny dust particles levitated above the main ring plane by electrostatic forces. They form and dissipate over periods of hours, and their exact mechanism is still not fully understood even today. Voyager also discovered new moons around Saturn, including some that orbit within the rings themselves, acting as shepherd moons that keep the ring particles in place. These shepherd moons use their gravity to confine the ring particles to narrow bands. For example, the F-ring, one of the narrow rings in Saturn's system, is shepherded by two small moons named Prometheus and Pandora. Prometheus orbits just inside the F-ring, and Pandora orbits just outside. Their gravitational influence keeps the ring particles from spreading out, maintaining the ring's narrow width. But the interaction is more complex than simple shepherding. The moons also create waves and kinks in the ring, and sometimes they even pull streamers of material out of the ring, creating temporary arcs and clumps. One of the most surprising discoveries at Saturn was the complexity of the moon Titan. Titan is Saturn's largest moon, bigger than the planet Mercury. It's the only moon in the solar system with a thick atmosphere, one that's even denser than Earth's. Titan's atmosphere is about 1.5 times as thick as Earth's at sea level. It's composed mostly of nitrogen, just like Earth's atmosphere, but with about 5% methane and traces of other hydrocarbons. The methane in Titan's atmosphere is particularly interesting because methane breaks down quickly when exposed to sunlight. This means there must be some process replenishing the methane, otherwise it would have disappeared long ago. Scientists think Titan might have methane volcanoes, structures that erupt liquid methane from beneath the surface, similar to how water volcanoes erupt on Earth. But Titan's atmosphere is so thick and hazy that Voyager couldn't see through it to the surface. The visible light images showed nothing but a featureless orange haze. It wasn't until the Cassini mission in 2004, which carried infrared cameras and radar, that scientists were able to peer through the haze and see Titan's surface. What they found was astonishing: a world with lakes and rivers and rain, but made of liquid methane and ethane instead of water. Titan is the only place in the solar system, other than Earth, where we know there are stable bodies of liquid on the surface. It's a bizarre alien world, where the temperature is minus 290 degrees Fahrenheit, where rocks are made of water ice as hard as granite, and where liquid methane plays the role that water plays on Earth. Voyager's images of Titan, limited though they were, sparked decades of scientific interest that eventually led to the Cassini-Huygens mission. The Huygens probe, built by the European Space Agency, actually landed on Titan's surface in January 2005, becoming the first and only spacecraft to land in the outer solar system. The images and data it sent back during its brief 2-hour operation on the surface showed a landscape of rounded pebbles made of water ice, sitting in damp soil made of hydrocarbon sand. It was a landing site that looked eerily similar to a dry riverbed on Earth, but with chemistry and temperatures that were completely alien. After leaving Saturn, Voyager 1 continued to send back data about the solar wind, the stream of charged particles flowing out from the Sun. The solar wind is essentially the Sun's outer atmosphere, expanding into space. The Sun's corona, the outermost layer of its atmosphere, is so hot that the Sun's gravity can't hold on to it. Temperatures in the corona reach about 1 to 2 million degrees Fahrenheit. At these temperatures, atoms are moving so fast that they can escape the Sun's gravity entirely. They stream outward into space at speeds of about 250 to 450 miles per second, carrying with them the Sun's magnetic field. This creates a bubble around the solar system called the heliosphere. Inside this bubble, the solar wind dominates. Outside, the interstellar medium takes over. Voyager measured how the solar wind changes as you move farther from the Sun, how it interacts with the interstellar medium, and where the boundary between the two lies. As Voyager traveled farther from the Sun, scientists observed the solar wind gradually weakening. At Earth's distance, the solar wind has a density of about 5 to 10 particles per cubic centimeter and moves at about 250 miles per second. By the time you reach Jupiter's orbit, the density has dropped to about 1 particle per cubic centimeter, but the speed remains roughly the same. At Saturn's orbit, it's even more dilute. And as Voyager continued outward, the solar wind became so thin that individual measurements became noisy and unpredictable. The spacecraft was approaching the edge of the heliosphere, where the solar wind begins to slow down and interact with the interstellar medium. This boundary region is called the heliosheath. It's where the solar wind, which has been traveling outward at supersonic speeds, suddenly encounters the pressure of the interstellar medium and slows down to subsonic speeds. When a fluid or gas goes from supersonic to subsonic, it creates a shock wave. This happened to Voyager in December 2004 when it crossed the termination shock, the point where the solar wind becomes subsonic. The crossing was dramatic. Voyager's instruments detected a sudden jump in the density and temperature of the solar wind plasma. The magnetic field strength increased. The intensity of low-energy particles dropped while high-energy cosmic rays from interstellar space increased. All the signs indicated that Voyager had crossed a major boundary. For several years after crossing the termination shock, Voyager continued through the heliosheath. This is a turbulent region where the solar wind is compressed and heated by its interaction with the interstellar medium. The plasma in the heliosheath sloshes back and forth, sometimes flowing inward toward the Sun, sometimes outward away from it. The magnetic field is tangled and twisted. It's a chaotic region, unlike anything in the inner solar system. Then, in August 2012, Voyager 1 crossed the heliopause and entered interstellar space. This was a historic moment. For the first time, a human-made object had left the solar system, in the sense that it had crossed the boundary where the Sun's influence gives way to the influence of the galaxy. The crossing wasn't as dramatic as the termination shock. There was no sudden jump in measurements. Instead, over a period of about 1 day, Voyager observed a gradual decrease in solar wind particles and a corresponding increase in galactic cosmic rays. The solar wind particles, which had been the dominant component of the plasma around Voyager, essentially disappeared. They dropped from a few particles per cubic centimeter to nearly zero. At the same time, the cosmic ray intensity increased by about 9%. These cosmic rays, high-energy particles from outside the solar system, had been partially blocked by the solar wind and magnetic field. Once Voyager crossed into interstellar space, it was fully exposed to them. The data Voyager sent back from interstellar space has been fascinating. It's shown that the interstellar medium is filled with low-frequency plasma waves, ripples in the charged particles that fill the space between stars. These plasma waves are analogous to ocean waves, but instead of water molecules, they're oscillations in ionized gas, electrons and ions moving collectively in response to electromagnetic forces. The waves have frequencies measured in kilohertz, far below what the human ear can hear, but when converted to audio and sped up, they create eerie whistling and humming sounds. NASA has actually released audio recordings of these plasma waves, and they're fascinating to listen to. They sound like science fiction sound effects, oscillating tones that rise and fall, sometimes punctuated by sudden bursts of static-like noise. But these aren't artificial sounds, they're actual recordings of the electromagnetic environment in interstellar space, translated into audio frequencies that humans can perceive. Voyager has also measured the density of this interstellar plasma and found that it's slightly higher than expected. Models predicted that the interstellar medium would have a density of about 0.05 particles per cubic centimeter. Voyager's measurements show it's closer to 0.08 to 0.1 particles per cubic centimeter. That might not sound like a big difference, but it has implications for how we understand the structure of the local interstellar medium. A higher density means more pressure, which affects how the heliosphere interacts with its surroundings. It also means that the region of space immediately around the solar system is slightly different from the average properties of the interstellar medium throughout the galaxy. We live in what's called the local interstellar cloud, a region of space that's slightly denser and slightly warmer than the average. This cloud is about 30 light-years across, and the solar system has been inside it for the past 40 to 50,000 years. We'll continue through it for another few thousand years before emerging into a different region with different properties. Voyager has also detected cosmic rays, high-energy particles that come from outside the solar system, and measured how their intensity changes as you move away from the sun. Cosmic rays are fascinating objects. They're not rays at all, despite the name. They're particles, mostly protons, but also heavier atomic nuclei like helium, carbon, and iron. They travel through space at nearly the speed of light, carrying enormous amounts of energy. The most energetic cosmic rays ever detected have energies comparable to a baseball thrown at 100 miles per hour. But all that energy is concentrated in a single subatomic particle. Where do these cosmic rays come from? Lower energy cosmic rays are produced by the sun, especially during solar flares. But the high-energy cosmic rays that Voyager detects in interstellar space come from much more violent events. Most are produced by supernova explosions, the catastrophic deaths of massive stars. When a star explodes, it releases more energy in a few seconds than the sun will produce in its entire 10 billion-year lifetime. This energy accelerates particles to relativistic speeds, creating cosmic rays. Some cosmic rays might come from even more exotic sources, like the jets of supermassive black holes at the centers of galaxies, or from the annihilation of dark matter particles. The highest energy cosmic rays, the real monsters, with energies millions of times higher than anything we can produce in particle accelerators, probably come from outside our galaxy. They might be accelerated in the jets of active galactic nuclei, powered by supermassive black holes consuming matter at prodigious rates. Or they might come from gamma-ray bursts, the most energetic explosions in the universe since the Big Bang. We don't know for sure because when a cosmic ray travels through the galaxy, it gets deflected by magnetic fields, which changes its direction. By the time it reaches Earth or Voyager, it's impossible to trace it back to its source. It's like trying to figure out where a pinball came from by watching it bounce around inside a pinball machine. Voyager's measurements of cosmic rays in interstellar space help us understand how these particles travel through the galaxy and how the Sun's magnetic field shields the inner solar system from them. The data shows that the cosmic ray intensity in interstellar space is about 3 to 4 times higher than it is in the inner solar system. This means the heliosphere is doing a reasonably good job of deflecting cosmic rays, but it's not perfect. Some still make it through, and they can pose a radiation hazard to astronauts on long-duration missions. If humans ever travel to Mars or beyond, cosmic ray radiation will be one of the major challenges to overcome. All of this data has helped scientists understand the nature of the space between stars, a region that we can only study directly by sending spacecraft out there. And Voyager has been the only spacecraft to do that so far. Voyager 2 crossed into interstellar space in November 2018, about 6 years after Voyager 1. It's taking a slightly different path through the heliosphere, and its instruments measured some things that Voyager 1 couldn't, because certain instruments were already shut down on Voyager 1 by the time it crossed the heliopause. Together, the two Voyager spacecraft are giving us a three-dimensional picture of the boundary between the solar system and interstellar space. They're showing us that the heliopause isn't a smooth spherical surface. It's irregular and dynamic, changing over time in response to variations in the solar wind and the interstellar medium. When the Sun is more active, putting out more solar wind, the heliosphere expands. When the Sun is less active, the heliosphere shrinks. The Voyager spacecraft are navigating through this changing boundary, and their measurements are helping us understand how our solar system breathes in and out in response to the Sun's 11-year activity cycle. Beyond the scientific discoveries, Voyager's journey through interstellar space has a deeper significance. It represents humanity's first step beyond the solar system, the first time we've sent something to the stars. It's a tiny step, barely out the door, but it's a step nonetheless. And it opens the possibility, however remote, that someday we might follow. There's something deeply poignant about Voyager's journey. This spacecraft, built by humans in the 1970s, using technology that now seems ancient, has traveled farther than anything else we've ever made. It's left the solar system, crossed into interstellar space, and it's still going, but it's dying. Slowly, quietly, inevitably, its power is fading. One by one, its systems are being shut down. Its instruments are going silent, and soon it will have no power left at all. It will drift through space in absolute darkness, its radio silent, its computers inactive, its mission over. But, in another sense, its mission will never be over, because, even after it goes silent, Voyager will continue to exist as a physical object. It will carry the golden record with it, a testament to the people who built it. It will drift through the galaxy for billions of years, outlasting civilizations, stars, planets, maybe even galaxies. It's a monument to human curiosity and ambition. We built this machine, we launched it into space, and we sent it on a journey that will never end. There's something profound about that. We are mortal. Our lives are brief, our civilizations fragile. But we can create things that outlast us. We can send messages into the future, messages that might be found by someone or something we can't even imagine. We can reach out across the vast emptiness of space and time and say, we were here, we existed, we wondered what was out there. And that's what Voyager represents. It's not just a spacecraft. It's a statement. A declaration that we are a species that looks up at the stars and asks questions. That we are curious, ambitious, hopeful, that we dare to explore the unknown, even though we know we'll never see the end of the journey. Let's bring this back to the numbers, because the scale of Voyager's journey is important to understand. Right now, Voyager 1 is about 14.5 billion miles from Earth. Light from the spacecraft takes about 21 hours and 30 minutes to reach us. That means, when NASA sends a command to Voyager, it takes 21.5 hours for the signal to arrive, and then another 21.5 hours for the spacecraft's response to come back. A total of about 43 hours for a round-trip communication. By 2036, when Voyager is expected to run out of power, it will be about 17 to 18 billion miles from Earth. At that point, light travel time will be about 26 to 27 hours each way. Voyager is traveling at about 38,000 miles per hour. That's fast, but it's still only about 0.0057% of the speed of light. At this speed, it would take Voyager about 73,000 years to travel 1 light-year. The nearest star, Proxima Centauri, is 4.24 light-years away, so it would take Voyager about 309,000 years to reach Proxima Centauri if it were headed in that direction, which it's not. Instead, Voyager is headed toward the star, Gliese 445, which it will pass in about 40,000 years. But remember, by that time, Voyager will have been dead for over 38,000 years. It will be a dark, silent hulk drifting through space, its mission long over, its creators long gone. And yet, it will still be moving, still carrying the golden record, still existing as a physical testament to the species that built it. One of the questions people often ask is whether we'll ever catch up to Voyager. Could we build a faster spacecraft and send it out to retrieve Voyager 1? It's a question that speaks to a deep human impulse, the desire not to let go, to retrieve what we've sent out into the void. Technically, yes, we could build a spacecraft that travels faster than Voyager. In fact, we already have. The Parker Solar Probe, launched in 2018, has reached speeds of over 430,000 miles per hour as it dives close to the Sun. That's more than 10 times faster than Voyager. At its peak velocity during close approaches to the Sun, Parker Solar Probe is the fastest human-made object ever built. It achieves these speeds by using the Sun's gravity in a series of carefully planned flybys of Venus. Each Venus flyby adjusts the probe's orbit, bringing it closer and closer to the Sun. And as it gets closer, it speeds up, like a skater pulling their arms in to spin faster. At perihelion, the closest point in its orbit to the Sun, Parker Solar Probe screams past at speeds that would let it travel from New York to Los Angeles in less than 30 seconds. But speed relative to the Sun isn't the same as speed through interstellar space. The Parker Solar Probe is using the Sun's gravity to accelerate. It's falling toward the Sun, converting gravitational potential energy into kinetic energy. If you wanted to send a spacecraft out to catch up with Voyager, you'd need to accelerate it in the opposite direction, away from the Sun, and that's much harder. You'd need enormous amounts of fuel, or you'd need to use some kind of advanced propulsion system, like ion drives or nuclear propulsion. Ion drives work by accelerating ions charged particles to extremely high velocities using electric fields. They produce very little thrust compared to chemical rockets, but they're incredibly fuel efficient. They can run for years, slowly but steadily accelerating the spacecraft to higher and higher speeds. NASA's Dawn mission, which visited the asteroids Vesta and Ceres, used ion propulsion. Over the course of its mission, Dawn's ion drive changed the spacecraft's velocity by more than 25,000 miles per hour, far more than any chemical rocket could achieve with the same amount of fuel. But even with ion drives, catching up to Voyager would be a monumental challenge. Voyager has a 48-year head start and is already 15.5 billion miles away. Any spacecraft we launch now would need to not only match Voyager's speed, but exceed it by enough to close the distance. Let's do some rough math. Voyager is moving at about 38,000 miles per hour. If we launched a spacecraft today that could accelerate to, say, 100,000 miles per hour, it would be moving 62,000 miles per hour faster than Voyager. To close 15.5 billion miles at a relative speed of 62,000 miles per hour would take about 28 years. So we'd catch up to Voyager around 2054, about 28 years from now. By that time, Voyager will have been dead for about 18 years. We'd be retrieving a piece of space junk, not a functioning spacecraft. And even reaching 100,000 miles per hour is no small feat. It would require either a very large, very powerful rocket or a long period of acceleration using ion drives or some other efficient propulsion system. Nuclear propulsion might be the answer. There have been proposals for nuclear thermal rockets that heat hydrogen propellant using a nuclear reactor. These could theoretically achieve much higher exhaust velocities than chemical rockets, allowing faster acceleration with less fuel. There are also concepts for nuclear pulse propulsion, where the spacecraft detonates small nuclear bombs behind it and rides the shockwave. This sounds insane, and it kind of is, but the physics actually work. Each nuclear detonation imparts a kick to a massive shock absorber plate at the back of the spacecraft, and these repeated kicks accelerate the ship to enormous velocities. Calculations suggest that a nuclear pulse propulsion spacecraft could reach speeds of several percent of the speed of light, potentially up to 10% if you were willing to use a truly massive ship with thousands of nuclear bombs. At 10% of the speed of light, you'd be traveling at about 67 million miles per hour. At that speed, you could reach Voyager in less than a day. You could fly out to interstellar space, retrieve the spacecraft, and bring it back to Earth, putting it in a museum where future generations could see the actual hardware that traveled farther than anything else we've ever built. It's a romantic idea, but it's also impractical. Building a nuclear pulse propulsion spacecraft would require an enormous investment, probably comparable to or greater than the cost of the original Voyager mission when adjusted for inflation. And for what purpose? By the time we caught up to Voyager, it would have been non-functional for decades. All we'd be retrieving is a defunct machine, a relic. We could build a new, better spacecraft for less money and send it out to explore regions of space that Voyager will never reach. The truth is, we're not going to catch up to Voyager. We're going to let it go. And that's okay. That's actually beautiful in its own way. Voyager was never meant to come back. It was always a one-way mission. The spacecraft was designed to fly past the outer planets, send back data, and then continue on into interstellar space. There was never a plan to retrieve it, never an expectation that it would return. From the very beginning, Voyager was meant to be our emissary to the stars, a traveler that would never come home. And there's something profound about that. We built this machine. We sent it out into the cosmos, and we said goodbye, knowing we'd never see it again. It's like a child growing up and leaving home, going out into the world to make their own way. You pour your love and care and knowledge into them, you send them off, hoping they'll do well, and then you let them go. You don't follow them everywhere they go. You don't try to bring them back. You let them live their own life, make their own journey. That's what we've done with Voyager. We gave it the best technology we had in 1977. We programmed it with instructions and safeguards. We launched it on a trajectory that would take it past Jupiter and Saturn and out into the galaxy. And then we let it go. We tracked it for as long as we could, listened to its signals, received its data. But eventually, the signals will stop. The power will run out. And Voyager will continue on alone, beyond our reach, beyond our ability to communicate or control. And that's the way it should be. Because Voyager's journey isn't really about the spacecraft itself. It's about what the spacecraft represents. It represents our curiosity, our desire to explore, our willingness to invest in projects that won't pay off in our lifetimes. It represents our hope that we're part of something larger than ourselves, a cosmic story that extends far beyond our individual lives. The scientists and engineers who built Voyager knew that they probably wouldn't live to see the spacecraft's final moments. They knew that Voyager would outlast them, continuing its journey long after they were gone, and they were okay with that. They built it anyway, because the mission wasn't about personal glory or immediate results. It was about contributing to humanity's understanding of the universe. It was about reaching out across space and time to touch the cosmos, even if only for a moment. That's why we won't chase after Voyager to bring it home, because Voyager is home. Not our home, but its home. The galaxy is where it belongs now. It's a creature of interstellar space, drifting among the stars, carrying its message from Earth to whoever or whatever might find it billions of years from now. We made our peace with Voyager's departure when we launched it in 1977. And when it goes silent in the 2030s, we'll make our peace with that too. We'll listen to the final transmission, whatever it may be. We'll watch the signal fade. We'll say goodbye one last time. And then we'll turn our attention to other missions, other spacecraft, other ways of exploring the universe. Because that's what we do. We're explorers. We send out missions knowing they'll end. We build spacecraft that will eventually fail. We launch telescopes that will someday shut down, and then we build new ones and start again. Each mission builds on the last. Each spacecraft teaches us something that informs the next design. Each discovery opens new questions that drive new investigations. Voyager taught us how to build spacecraft that could survive for decades in deep space. It taught us about the outer planets and their moons. It taught us about the boundary between the solar system and interstellar space. And all of that knowledge has gone into newer missions. New Horizons, which flew past Pluto in 2015, was designed with lessons learned from Voyager. The Cassini mission to Saturn, which operated from 2004 to 2017, built on Voyager's discoveries. Future missions to the outer solar system and beyond will continue this tradition. Each one pushing a little farther, lasting a little longer, discovering a little more. And somewhere out there, Voyager will be drifting, silent and dark, but still moving, still carrying the golden record, still representing everything we hope to achieve when we first looked up at the stars and wondered what was out there. That's Voyager's true legacy. Not the data it collected, as valuable as that data is. Not the images it sent back, as beautiful as they are. But the fact that it exists at all. The fact that we built it and sent it on its way. The fact that we dared to reach beyond our planet, beyond our solar system, and touch the stars. Even if only with a machine. Even if only for a few decades of active operation. We reached out. We tried. We sent a piece of ourselves into the cosmos. And that piece is still out there, still traveling, still carrying our message. And it always will be. There's another aspect of Voyager's journey that's worth considering: the psychological impact. For the scientists and engineers who work on the Voyager mission, this spacecraft is more than just a machine. It's a part of their lives. Some of them have been working on Voyager for decades. They've guided it through planetary flybys, troubleshot problems, managed its declining power, and coaxed it to keep going year after year. When Voyager finally goes silent, it will be an emotional moment for these people. It will be like saying goodbye to an old friend. And, in a way, it is. Voyager has been a constant presence in their lives, a connection to something larger than themselves. For the rest of us, Voyager's silence will mark the end of an era. It will be the end of the only mission that has ever taken a spacecraft beyond the solar system and into interstellar space. The end of the only mission that has sent us data from a region of space that we can't study in any other way. And it will be a reminder of our limitations. We are bound to this planet, to this solar system. We can send machines out into the galaxy, but we ourselves cannot follow. Not yet, anyway. Not with our current technology. Maybe someday that will change. Maybe someday humans will travel to the stars. Maybe someday we'll catch up to Voyager and bring it home, put it in a museum, show our descendants the little machine that started it all. But for now, Voyager is on its own. And when it goes silent in 2036, it will truly be alone, drifting through the galaxy for billions of years, carrying its golden message from a planet called Earth. Let's talk about what happens to Voyager's physical structure over extremely long timescales. We've established that Voyager will drift through space, essentially forever. But what about the spacecraft itself? Will it remain intact, or will it eventually disintegrate? Over the next few thousand years, Voyager will remain largely unchanged. The materials it's made of, aluminum, titanium, stainless steel, copper, gold, are stable in the vacuum of space. There's no oxygen to cause corrosion, no water to cause rust, no biological organisms to cause decay. The spacecraft will look almost exactly the same in 10,000 years as it does today. But over longer timescales, things start to change. Cosmic rays, high-energy particles that zip through the galaxy at nearly the speed of light, will gradually bombard Voyager. Each cosmic ray that hits the spacecraft will deposit a tiny amount of energy, potentially knocking atoms out of place and creating defects in the material's crystal structure. Over millions of years, this cosmic ray damage will accumulate. The metals will become more brittle. The electronics, already non-functional, will degrade further. The golden record's surface might become pitted and scratched. But the spacecraft will still be recognizable as a human-made object. It will still have its distinctive shape, its antenna dish, its scientific instruments, its golden record. Over billions of years, the damage will continue to accumulate. Eventually, perhaps after tens of billions of years, the spacecraft might begin to fragment. Pieces might break off. The structure might collapse. But this process will be incredibly slow. There's no weather in space, no wind or rain to erode the spacecraft. Just the slow, steady bombardment of cosmic rays and the occasional micrometeoroid impact, if proton decay is real. And that's still a big if. Then over timescales of 10 to the 34 years or longer, even the atoms that make up Voyager will decay into radiation. At that point, Voyager will truly cease to exist as a physical object. But that's so far in the future that it's almost meaningless to think about. For all practical purposes, for timescales that we can actually wrap our minds around, Voyager will exist forever. There's something almost mythological about Voyager's journey. It's reminiscent of the ancient Greek myth of the ship of Theseus, or the Norse myth of the world tree Yggdrasil, or countless other stories about journeys into the unknown. Voyager is our modern myth. It's the story of a small machine built by curious beings on a small planet, sent out into the vastness of space on an endless journey. It's a story about exploration, about pushing boundaries, about reaching beyond our grasp. And like all good myths, it has a bittersweet ending. Voyager will go silent. Its mission will end, but its journey will continue. And in continuing, it will carry with it the hopes and dreams of the species that built it. Every generation has its defining moments, its achievements that capture the imagination and inspire future generations. For the generation that built Voyager, this spacecraft was one of those achievements. It represented the pinnacle of what was possible with the technology of the time. It showed that humans could build machines that could travel to the outer planets, could function for decades in the harsh environment of space, could send back data from regions never before explored. And it showed that we could dream big, that we could look up at the stars and say, "We want to go there. We want to see what's out there. We want to reach out and touch the cosmos." Voyager is proof that we can do those things. Not easily, not cheaply, not quickly, but we can do them. We can build machines that outlast us. We can send messages that will survive long after we're gone. We can leave a mark on the universe. The scientists working on Voyager are already preparing for the end. They know it's coming. They know that within the next 10 to 15 years, they'll have to shut down the last instruments. They know that within the next 20 years, they'll lose contact with the spacecraft completely, and they're making plans for how to handle it. There will be a final transmission from Voyager, a last signal sent back to Earth before the power runs out. NASA hasn't decided yet what that final transmission will say, or even if it will say anything at all. It might just be a carrier signal, a simple tone that says, "I'm still here." Or it might be something more meaningful, a final message crafted by the mission team, a goodbye from Voyager to the species that built it. Either way, it will be a moment of significance, the end of one of the most successful missions in the history of space exploration. When that moment comes, the Deep Space Network will listen as the signal from Voyager fades away. The scientists will watch their screens as the data stops coming in, and then there will be silence. No more transmissions, no more data. Just the faint background hiss of the universe, and Voyager will be gone, at least from our perspective. It will still be out there, still moving, still carrying the golden record, but we won't be able to hear it anymore. We won't know where it is, what it's doing, whether it's still intact. It will have passed beyond our reach, beyond our ability to observe or communicate with. It will be truly alone. Let's return to the central question one more time. How far can Voyager 1 travel before it dies? The answer, as we've seen, depends on what you mean by dies. If you mean when it stops sending scientific data, that will happen in the next 5 to 10 years, at a distance of about 15 to 16 billion miles from Earth. If you mean when it stops transmitting any signal at all, that will happen around 2036, at a distance of about 17 to 18 billion miles from Earth. If you mean when it stops being a recognizable physical object, that might not happen for billions of years, or even trillions of years if proton decay doesn't occur. And if you mean when it stops moving, well, that will never happen. Voyager will continue to drift through space, essentially forever, moving at 38,000 miles per hour through the galaxy, visiting no particular destination, just traveling endlessly through the void. So the answer is both finite and infinite. Voyager will die in the sense that it will stop functioning, stop transmitting, stop being useful as a scientific instrument. That death is coming soon, within the next 10 to 20 years. But Voyager will also live forever in the sense that it will continue to exist as a physical object, continue to move, continue to carry the golden record, continue to be a testament to the species that built it. It's a paradox, but it's a meaningful one. Voyager is mortal and immortal at the same time, just like us. We are mortal as individuals. Our lives are brief, measured in decades, but we are also immortal in the sense that we can create things that outlast us. We can write books that will be read centuries from now. We can build buildings that will stand for millennia. We can send spacecraft to the stars that will drift for billions of years. We can leave a mark. And Voyager is that mark. It's our message to the future, our proof that we were here, that we existed, that we wondered and explored and dreamed. It's a small machine, barely the size of a car, but it carries the weight of an entire civilization's hopes. One last thought. Voyager 1 is currently the most distant human-made object from Earth, but it won't hold that record forever. Voyager 2 launched 16 days before Voyager 1, but traveling on a slower trajectory is currently a bit closer to Earth. But Voyager 2 is also dying. Its power is declining at the same rate as Voyager 1's. It will also go silent in the mid-2030s. And then there are the other spacecraft. Pioneer 10 and Pioneer 11, launched in the early 1970s, are also drifting through interstellar space. They lost contact with Earth decades ago, but they're still out there, still moving. New Horizons, which flew past Pluto in 2015, is on a trajectory that will take it out of the solar system. It's traveling faster than Voyager relative to the Sun, and it still has power and is still communicating with Earth. In a few thousand years, New Horizons will overtake Voyager as the most distant human-made object, and then, eventually, New Horizons will also die. Its power will run out, its systems will shut down, and it will drift silently through space, just like Voyager. And maybe, someday, we'll launch other missions. Faster spacecraft, better equipped, with more advanced technology. Maybe we'll send probes to other stars, to Alpha Centauri, or Proxima Centauri, or Barnard's star. Maybe we'll even send humans. Maybe our descendants will travel to the stars, and tens of thousands of years from now, they'll find Voyager. They'll recognize it as an artifact from their ancient past, a relic from a time when humanity was just beginning to reach out into space. They'll recover the golden record and play it, and they'll hear the sounds of Earth, the greetings in 55 languages, the music from Beethoven and Chuck Berry, the sounds of thunder and waves and bird calls. and they'll remember where they came from. They'll remember the small planet that gave birth to their species, the planet that looked up at the stars and decided to reach out. That's the legacy of Voyager. Not just the scientific data it collected, not just the images it sent back, but the fact that it exists at all. The fact that we built it, launched it, and sent it on an endless journey into the unknown. That's the real achievement. That's what makes Voyager special. It's proof that we are a species that explores, that questions, that reaches beyond our grasp. And that's something worth celebrating. So here we are at the end of this journey, at least for tonight. Voyager 1 is out there right now, 15.5 billion miles from Earth, moving through interstellar space at 38,000 miles per hour. It's sending back data, though that data is faint and getting fainter. It's operating on borrowed time, its power declining by 4 watts every year. And soon, within the next 10 to 20 years, it will go silent. It will run out of power, shut down its systems, and drift into the darkness. It will travel about 17 to 18 billion miles before it dies, a distance that's enormous by human standards, but minuscule by cosmic standards. Less than 3/1000ths of a light year. Less than 1/10,000th of the distance to the nearest star. But it will keep moving. Long after it's dead, long after we're gone, it will keep traveling through the galaxy. 40,000 years from now, it will pass within 1.6 light years of the star Gliese 445. Billions of years from now, it will still be drifting, still carrying the golden record, still existing as a testament to the species that built it. Voyager will outlast our cities, our civilizations, our entire species. It will outlast Earth itself. It will outlast the sun. And in doing so, it will carry a piece of humanity into the deep future, into a time and place we can barely imagine. That's how far Voyager can travel before it dies. 17 billion miles until its power runs out. Trillions and trillions of miles after that, drifting forever. And somewhere in between, it will pass from being a functioning spacecraft to being something else. A relic, a monument, a message in a bottle floating in the cosmic ocean. It's a beautiful, sad, hopeful story. And it's our story. The story of what we can achieve when we dare to explore, when we dare to dream, when we dare to send a small machine into the vastness of space and say, "This is who we are. This is what we've done. Remember us." Thank you for joining me on this journey tonight. I hope you found it as fascinating as I do. The story of Voyager is one of the great achievements of our species, and it deserves to be remembered and celebrated. If you enjoyed this exploration, please like this video and subscribe to the channel. It helps more than you know. And the next time you look up at the night sky, take a moment to think about Voyager. It's out there right now, farther from Earth than anything else we've ever built, traveling through the darkness, carrying our message to the stars. It's dying, but it's also living forever. And in that paradox, there's something profound about what it means to be human. Good night, and keep looking up. The universe is vast, but we're part of it. And Voyager, small and fragile as it is, proves that we can reach out and touch the cosmos. Even if just for a moment, even if just with a machine, we can reach out. And that's something special.